Welcome back to Module 5, Blockchain, Security and Digital Identity. In this lecture, we will explore identity management and access control models of blockchain-based applications. We will look into identity management principles in traditional applications and identity management in blockchain networks, access control in traditional networks and access control mechanisms in blockchain networks. We will also look into the privacy mechanisms in blockchain networks, and we will explore blockchain-based personally identifiable information and self-sovereign identity. According to CHAISE learning outcome, after this lecture, you will be able to explain the identity management principles of blockchain networks as well as the access control models in blockchain networks. You will be able to explain blockchain-based personally identifiable information and self-sovereign identity. This lecture has three main learning objectives. First, to explore the identity management principles in traditional and blockchain-based applications, as well as to explore access control models in traditional and blockchain networks, and to present blockchain-based personally identifiable information and self-sovereign identity. So, let us get started. Identity management is a fundamental, or we can say like identity is a fundamental asset of interaction. So, the identity management, also known as identity and access management, ensures that authorized people have access to the resources. Identity management is all about managing the identity attributes of individuals, for example, name, national identifier, social security number, and there are many more such identity attributes. And it also the identity attributes also belongs to companies, for example, like for managing sensitive user information to fulfill privacy regulations like GDPR. Once using Internet of Things devices, for example, like identity management of connected sensors, monitors and devices and managing sensitive data access. Identity management enables the process of identifying, authenticating and authorizing users to access services. For example, customers or employees have access privileges and restrictions while accessing software or hardware inside the company. In traditional networks, identity management is handled through a centralized database where a centralized and designated authority or administrator controls the creation and management of identities. For example, a centralized mechanism for credential issuance and verification. Some centralized systems use third-party services for identity issuance and verification, and users have no ownership or control or protection over their identities and the privacy they deserve. There are various cases in traditional systems where data linking poses serious security threats when sensitive information and personal details are linked. For example, personal healthcare records and banking transactions. There are various challenges of identity management in traditional networks. For example, taking the discussion from the last slide, there are numerous challenges associated with identity management in traditional networks. For example, like inaccessibility, where users cannot have control over identifiable information. Moreover, around 1.1 billion people around the globe don't have proof of identity at all. There are risks of data insecurity. For example, tampering is an utmost concern where unauthorized users can make malicious modifications to the data. Data theft, breaches and social engineering are some techniques that lead to data leakage or disclosure. The data loss cases are heightening because users forget their usernames or passwords, and it is difficult to remember multiple usernames and passwords. There are single point failures when identity data is required. Malicious attackers create fraudulent identities, for example, to operate malicious activities over the internet. Know your customer or KYC onboarding is a scalability limitation where processing invoices with multiple stakeholders, for example, like verifying companies, KYC companies, users and third parties, make it expensive process. So, no association between the Bitcoin, the identity management in Bitcoin network is handled through various techniques. For instance, like no association between the Bitcoin addresses and any user's identity that makes Bitcoin pseudonymous. For example, like the user identity is linked with a cryptographic address. So, the ownership within the Bitcoin platform is established through digital keys, Bitcoin addresses and digital signatures. Users are identified by their Bitcoin addresses, not by their name or by email. A Bitcoin address represents the ownership of a private and public key pairs, for instance, like PKI, public key infrastructure, and it allows nodes to authenticate each other's identity using elliptic curve digital signature algorithm, which enables peer-to-peer authentication. Identity management in Ethereum network is similar to Bitcoin. In Ethereum, there is no association between the Ethereum addresses and any user's identity. Ownership within the Ethereum platform is established through digital keys, Ethereum addresses and digital signatures. Users are identified by their Ethereum addresses. An Ethereum address represents the ownership of a private and public key. For example, Ethereum nodes have to identify themselves with some basic information to connect to the peers. To ensure any potential peer can interrupt, or we can say like to ensure any potential peer can interpret this information, it is relied in one of three standardized formats that the Ethereum nodes can understand. For example, like multi-ADDR, eNode or Ethereum node records. Ethereum node records are the current standard of Ethereum network addresses. Multi-ADDR is a universal format designed for peer-to-peer networks. Addresses are represented as key value pairs with keys and values separated with /. An eNode is a way to identify an Ethereum node using a URL address format. The hexadecimal node ID is encoded in the username portion of the URL, separated from the host using an @ sign. The host name can only be an IP address. DNS names are not allowed. The port is the host name section in the TCP listening port. If the TCP and UDP ports differ, the UDP port is specified as query parameter disk port. Ethereum nodes records as a standardized format for network addresses on Ethereum. They supersede multi-ADDRs and eNodes. As I said, like Ethereum node is the current is the current standard for Ethereum network addresses. So these are like especially useful because they allow greater information exchange between nodes. The Ethereum node records contain a signature sequence number and fields detailing the identity scheme used to generate and validate signatures. Users on the Ethereum network are identified by their Ethereum addresses. Thus, Ethereum addresses represent the ownership of identity. Identity management in Hyperledger Fabric is slightly different how it implemented or how it is designed in Ethereum and Bitcoin network. In Hyperledger Fabric, the Hyperledger Fabric consists of the concept of digital keys, digital signatures, certificates and hashing that secure overall the Hyperledger Fabric ecosystem. Digital keys represent asymmetric cryptographic schemes that hold public and private keys. The private key signs the transaction and produces digital signatures. The public key included in the transaction payload is sent to peers, or we can say like orders, then peers and orders verify the signatures using the public key in the transaction. An instance of public key infrastructure forms a membership service provider. certificate authority or certificate issuer signs the certificate of the party by their private key. In order to prove identity without revealing information about it, to make sure integrity of the certificate, for example, tampering will invalidate the certificate. In Hyperledger Fabric, authentication mechanism rely on digital signatures. Also, a digital signature is sent to peers and orders. Digital signatures also provide guarantees of the integrity of the signed message. Digital signature mechanisms require each party to hold two cryptographically public and private keys. Digital signature corresponding to the public key that recipients could verify. A digital signature is created by using the elliptic curve digital signature algorithm. In Hyperledger Fabric, digital certificates are issued by a certificate authority. A certificate authority is responsible for the registration of identities, issuance of enrollment certificates, certificate renewal, and revocation. Compliant with the X509 standard, and this standard defines the format of public key certificates. A digital certificate holds a set of attributes relating to a certificate holder. A membership service provider offers an abstraction of membership operations. It helps to manage identities, for example, authenticating clients who want to join the blockchain network. Membership service providers use certificate authority to provide identity verification. On the Hyperledger Fabric network, the membership service provider is a bunch of directories that contain digital certificates. Hyperledger Fabric provides a membership identity service that manages user IDs. The service authenticates all participants on the network. For example, Hyperledger Fabric uses X509 certificates to authenticate every entity and member in the network. Access control is an additional layer of permission that authorizes using specific network operations. For example, a specific user can be permitted to invoke a chain code application but be blocked from deploying a new chain code. Hyperledger Fabric working on the concept of trust ID. The trust ID would decentralize the identity within Hyperledger Fabric. So, the blockchain based identity management principle are providing various characteristics which are relevant, which we can say like are providing those characteristics by design. The blockchain is providing those characteristics by design. For instance, compared to traditional networks identity management principles, a blockchain based decentralized identity system provides ownership and user control over their identity security. The identity is immutable, tamper-proof, and auditable on decentralized networks. Identities are distributed, thus overcoming single point failure. For example, like once the identity information is required, so it will be available. Due to the distributed and decentralized nature, the management is cost effective. The management of identities is cost effective and can overcome the dependency on identity issuers and verifiers. For instance, like different organizations are using third parties or third party organizations for the issuance and verification of the user identities. So, this can in decentralized environment, this can be overcome. Furthermore, identities and identity creation process are transparent in decentralized environment. So, verifiable authenticity exists for every transaction. They are pseudo-anonymous, where masking true identity by using unique hash addresses, providing universal identity without geographically boundaries for identity management. The next concept is access control mechanisms in centralized networks and the access control mechanisms in blockchain networks. So, the access control is the selective restriction process, a selective restriction of access to a place or other resources. Access control is a security technique a mechanism that regulates individuals about who or what can access the resources. For instance, the authorized users to enable them to perform certain operations. Access control mechanism enables organization to manage who is authorized to access corporate data and resources. There are various kinds of access control mechanisms. For example, role-based access control, and this role-based access control mechanism we slightly discussed in our previous lecture as well, where we present the role-based access control mechanism in decentralized environment implemented using smart contracts. But this role-based access control mechanism you can also build in centralized applications, but the management is assigned to a single designated authority. Another kind of mechanism is attribute-based access control mechanism, then discretionary access control mechanism and mandatory access control mechanism. So, what are the challenges of access control mechanisms in traditional networks? In traditional networks, the first and foremost challenge related to access control is inconsistency. For example, defining access controls for specific users on specific resources and operations. Due to this, data or sensitive operations are disclosed to non-relevant users at on various times. Security risks associated with unauthorized access to a system where unauthorized users can gain access to sensitive information or perform actions within the system by exploiting its vulnerabilities, or simply obtaining access to elevated privilege accounts such as administrator accounts to get more access to the system resources. So, such security threats can pose a significant threat to the security and confidentiality of data stored in the system and can result in data breaches, loss of sensitive information and other malicious activities. So, centralized infrastructure that is prone to a single point of failure. Moreover, access control lacks granularity and scalability, as we previously stated in the case of inconsistency. Inter-device communication in a distributed network, for example, IoT devices, has different underlying authentication and authorization policies. Many systems still follow outdated infrastructure and their security patches are not implemented. So, how the access control is managed in Bitcoin networks? Bitcoin network is based on proof of work and does not rely on access control. The network can be open and no encryption is required for Bitcoin traffic or the nodes to join the network. Bitcoin is permissionless blockchain platform, so no permissions is required to become part of the Bitcoin network. Anyone from around the world can come to the blockchain network and join the blockchain network, and he can start participating in the Bitcoin network operations. In the Bitcoin platform, transactions are publicly available and anyone can see the transactions. Similar to Bitcoin, Ethereum access control mechanism in Ethereum is not much different. The Ethereum network is based on proof of stake, and again the Ethereum network does not rely on any access control mechanisms. The network is open and no encryption is required for Ethereum traffic. Ethereum is also an example of permissionless blockchain platforms, so no permission is required to become part of the Ethereum network. Anyone can join the network and start participating in the network operations. In the Ethereum platform, transactions are publicly available, similar to like Bitcoin, and anyone can see the transactions. However, in Ethereum based applications, there is a possibility to implement role-based access control using the Solidity programming language, for instance, like in the case building smart contracts. So, this smart contracts based role based access control mechanism can be built in Ethereum based applications. In contrast, Hyperledger Fabric uses access control lists to manage resources access. And Hyperledger Fabric access control mechanism is entirely different from permissionless blockchains. For instance, like we discussed Bitcoin and Ethereum. Because Hyperledger Fabric is a permissioned blockchain and it has various access control mechanisms incorporated within their network. For example, one is access control lists. So access control lists work based on the rule that elevates or evaluates to true or false. In Hyperledger Fabric, user chain codes. So previously we discussed chain codes are smart contracts but named chain code in the Hyperledger Fabric networks. So in Hyperledger Fabric, user chain code, event stream sources or system chain codes are considered resources. For example, if participant nodes request to call multiple system chain codes, then all of the access control list for those system chain codes must be satisfied. The list of resources is found in config.tx.yaml file. So once you are deploying or creating the system, a network of using Hyperledger Fabric, there is a file config.tx.yaml where you can see all the access control list and who can access different resources based on those access control lists. Hyperledger Fabric supports attribute-based access control. Default, there are two types of policies associated with resources. Firstly, they are signature policies, and secondly, there are implicit meta policies. So the blockchain-based access control mechanism, which is implemented in smart contracts and implements strong cryptography and data protection against various security and implementation challenges. Blockchain enables decentralized access control management, as we previously discussed. Security is provided through the built-in characteristics of blockchain, for example, immutability, tamper evidence, and auditability. The services are distributed and decentralized, therefore overcoming single point failures. Moreover, transparency due to the shared trust on untrusted distributed nodes all over the world. When we talk about identification, identity management, and access control, we also talk about privacy. For instance, the capacity of the user to control, access, and govern personal information is referred as privacy, or is referred to as privacy. So the privacy in Bitcoin, as previously we discussed, Bitcoin is pseudonymous, which means funds or transactions are not tied to real world entities, but rather to Bitcoin addresses. So the owners of Bitcoin addresses are not explicitly identifiable, but all transactions on the blockchains are public. Pseudonymity is achieved through using cryptographic addresses, and thus pseudonymity of a system as a private property to protect the user's identity. Users can generate as many key pairs as they want. For example, like having multiple Bitcoin addresses as users want, and it keeps the users from being linked and traced back to a common owner. Use Tor transport, which supports anonymity, untraceability, and privacy as an extra security layer when you are performing operations on Bitcoin network or any other blockchain network. For instance, like you are creating a crypto transaction, so use key pairs every time once you are creating a new transaction, and for the extra anonymity, use the Tor network. Privacy in Ethereum network, similar to Bitcoin, Ethereum is also pseudonymous. It means funds are not tied to real world entities but to Ethereum addresses. Owners of Ethereum addresses are not explicitly identified, but all transactions on the blockchain are public. So pseudonymity of a system as a private property to protect a user's identity. Users can generate as many key pairs, for example, like having multiple Ethereum addresses as users want, and it keeps a user from being linked and traced back to a common owner. In Ethereum, zero knowledge proofs is also available, but it's only available in enterprise Ethereum version. Moreover, you can bring the concepts of mixings. For example, like mixing techniques are available to obfuscate the transaction to protect against a de-anonymization attack. In Hyperledger Fabric, there exists a concept of private transactions. Hyperledger Fabric supports private data to keep the ledger data private from other organizations on the channel. Also, a chain code based access control logic restricts data access to certain roles by building chain code based access control logic. Hyperledger Fabric zero knowledge proofs makes anonymous client authentication with identity mixer and helps to implement a privacy preserving exchange of assets with zero knowledge asset transfer. So, till now we discussed identity management principles in traditional networks. We discussed identity management in blockchain networks, where we explored Bitcoin, Ethereum and Hyperledger Fabric. We also explored access control mechanisms in Bitcoin, Ethereum and Hyperledger Fabric. And now we are going towards blockchain based, or we can say like personally identifiable information, and how blockchain can play a role in personally identifiable information, as well as in the later part we will explore blockchain based self-sovereign identity. So, personally identifiable information is a data, or is data used to verify an individual's identity. For instance, email addresses, national identification number, passport number. So, personally identifiable information confirms an individual identity. However, there are various challenges in centralized nature of personally identifiable information. So, there are various, either like a design challenges or implementation challenges or security challenges. Here we will discuss more security challenges related to personally identifiable information. For example, malpractice. Malpractice means like holding sensitive personal details and negligence to investigate the correctness of those personally identifiable information over time. Second is identity theft, very common in the current digital realm. For example, like malicious attackers or malicious actors use someone's identity, for example, like name, identification number, credit card number, without permission to commit fraud or other crimes on the internet. Spamming is described as sending irrelevant or uninvited communications to a large number of internet users for illegal advertising and other activities such as phishing and virus distributions. So, this comes under like social engineering as well. Phishing, by Microsoft definition, phishing is an attack that tries to steal users' money or identity by tracking them to disclose personal information, such as credit card numbers, bank account numbers, passwords, usernames on websites that appear to be trustworthy. Cyber espionage, unauthorized users' attempts to access sensitive or classified data. Inaccessibility, due to the centralized nature and risk of single point failure, there are high chances of inaccessibility or impossible to reach due to the system overhead. The last one is difficult to track the flow and genuineness of personally identifiable information. So, here comes the blockchain based personally identifiable information. Blockchain based personally identifiable information takes the leverage of built-in blockchain based characteristics. For example, immutability, consensus mechanisms for decentralized verification and validation, consent through a smart contract, like you can build a consent terms using smart contracts, which is again like decentralized and distributed and immutable as well. So, any tampering in those consents can be identifiable by the blockchain network and discard those invalid changes, as well as decentralized operations where no central party is involved. So, for example, like no central authority, no central party or designated authority is controlling and managing your personally identifiable information. So, the completely your identities are decentralized, distributed, and you have the control over your identifiable information. Distributed ledger works on peer-to-peer network and the transmission that brings transparency and pseudonymity, where individual activities and identities are linked to cryptographic addresses. For instance, like we discussed many times now, blockchain or other blockchain networks, for instance, like Bitcoin, Ethereum, Hyperledger Fabric, they do not relate the transactions or data directly to the user's identifiable informations. For example, like email addresses, credit card numbers, or personally identification numbers. So they are the identities are linked to cryptographic addresses. So they are like pseudonymous, providing the pseudonymity. Moreover, the irreversibility of records. However, some issues still exist in blockchain-based personally identifiable information. For example, like having GDPR compliance, various applications used on and off chain storages to overcome this issue already for managing personally identifiable information, but still how the off-chain storage identities are authenticated, it depends again on the centralized systems. And if, for instance, like there are some changes happened, then off-chain stored identities maybe got corrupted. So there are still some limitations in blockchain-based personally identifiable information. But there is a lot of research is going on to explore new techniques within blockchain-based personally identifiable information techniques. Decentralized identifiers can be implemented in blockchain-based applications that provide pseudonymous identifiers secured by a private key, where a private key owner can prove that they own or control their identity. Users can have multiple decentralized identifiers, where each decentralized identifier associated with a series of attestations, for example, like verifiable credentials that are issued by other decentralized identifiers that attest to specific characteristics of that decentralized identifier. For example, like location, age, pay slips, diplomas, and like such kind of other information. Decentralized identifiers are cryptographically signed credentials. Self-sovereign identity, an interesting concept which is emerging within the blockchain, like using the blockchain, and it is an approach to digital identity that gives individuals control over their information. They use to prove who they are to, for instance, like they give individuals control over their information. They use to prove who they are using the websites, services, and applications across the web. And the people and businesses can store their identity data on their own devices as well. They are free to choose which piece of information to share with the validators without relying on a central repository of identity data. So very straightforward concepts, which is like belongs to self-sovereign identity, and blockchain can play a massive role in this domain. So in this lecture, we discussed the identity management in traditional network, identity management in blockchain-based networks like Bitcoin, Ethereum, and Hyperledger Fabric, and also we looked into like what type of characteristics and what type of benefits, advantages we have while using blockchain-based identity management. And then we discussed access control mechanisms, access controls in traditional network. We explored like there are various challenges, issues, and security threats that can be happen on traditional networks. So we present like blockchain-based access control mechanisms which blockchain-based networks are using, for instance, like Bitcoin, Ethereum, and Hyperledger Fabric. So we explored like Bitcoin and Ethereum have like similar kind of access control mechanisms in their networks, but Hyperledger Fabric is completely different because of their permissioned nature, and they are implementing various access control techniques within their networks. And at the end, we explored like how blockchain based access controls are implemented, or what type of characteristics and benefits they are providing overall to the blockchain based applications. Briefly, we discussed personally identifiable information and their challenges in the centralized environment, and then we present blockchain based personally identifiable information and what type of characteristics blockchain can provide to overcome this current security challenges of personally identifiable information. We also explored blockchain based personally identifiable information also have some different challenges, for instance like to comply with GDPR regulations, as well as the identifiable information which is stored on off-chain, the security aspects of that information. Then we discussed decentralized identifiers, where the users can have their decentralized identifiers, and self-sovereign identity, which can be emerging concept within blockchain, emerging concepts that can use blockchain to implement self-sovereign identity of users.